This is a lab4 report of microscopic view of DC and RC circuits produced by Shimiko. In this lab, I'll go through Introduction and Fundamental Theorem, section of Charge Conservation and Energy Conservation in Series Circuits, section of RC circuit, and the final evaluation of two what-if questions. Using the principle of energy conservation and current conservation, we try to predict the behavior of circuits containing resistors in series and parallel. Use multimeters that are ammeter and voltmeter to measure the actual values of conventional current and potential differences in circuits, and examine the behavior of ohmic resistors and capacitors. The fundamental theorem I applied in this lab is the conservation of energy and charge, respectively loop rule, node rule, and Ohm's rule. The first part will be charge conservation and energy conservation in series circuits. For this diagram, we can see that R total equals to 47 plus 100, that is 147 ohms. So the predicted current of both I1 and I2 are 2 times 1.5 divided by 147, that is 0.0204 amps. And by simulating the sample diagram into CCK, I observed the current to be 0.02 amps respectively, and inserted backwards the reading of ammeter reverses. By replacing one of the ammeter with a voltmeter, we can see that the reading of another ammeter goes to zero, and the voltmeter takes up all the 3 volts from the battery. This is because the resistance of voltmeter is so large that there is a small current of nearly zero, and the ammeter cannot measure it, and the large resistance leaves no potential difference for the other resistor. And from the observation before, the recorded current of I equals to 0.02 amps. My predicted potential difference for a round trip from A to A is 0 volt. To test this, I measure the potential difference between each intervals and get 3 volt, 0 volt, negative 0.959 volt, 0 volt, negative 2.041 volt, 0 volt, 0 volt, 0 volt, respectively. And adding up all the values, I get an actual potential difference of 0 volt, which is consistent to my prediction. And plugging in all the observed values here, I plot a graph of potential versus circuit position here. And for the extra questions of this section, when you attach the voltmeter, you alter the circuit. Why doesn't the ammeter reading change? This is because, similar to what we observed before, the circuit is negligible when connected to the voltmeter, no matter in what direction, so the reading won't change. Connect to a voltmeter across 100 ohms resistor again. What is the new ammeter reading? I observed that the new ammeter reading equals to 0.02 amps. And now replace the voltmeter with an ammeter in parallel with a 100 ohm resistor. What happens to the circuit through the other ammeter, and why? The current now becomes 0.06 amps because the ammeter is in parallel with the resistor and get a resistance of nearly zero. So the current will directly flow through the ammeter and disregard the 100 ohm resistor. So the current in the circuit will be larger than before. And the final calculation of the resistors are 47.95 ohm, 102.05 ohm, and 0 ohm, 0 ohm, respectively, for the 4 resistance. The second section is the RC circuit. These are my observations on the RC circuit. For the battery to the 10 ohm bulb and capacitor in series, light produced by the 10 ohm bulb starts bright and then dims and eventually goes out while the capacitor charges, and the current decreases and finally ends up in zero. When disconnecting the battery and connect the capacitor directly to the 10 ohm bulb, capacitor gives charge to the light bulb. The light goes from bright to dim while the current decreases, and eventually the capacitor is completely discharged and current goes to zero. The measured time and capacitor charges and discharges are: for the 10 ohm bulb, it takes 10.65 seconds to charge and 10.71 seconds to discharge. For the 20 ohm bulb, it takes 18.3 seconds to charge and 18.54 seconds to discharge. Time-dependent voltage across discharging capacitor. Based on the analytical deformation of equation, delta V capacitor plus delta V resistor equals to 0, based on the assumption that the electric field in the connecting walls is negligible, we get ln delta V divided by delta V0 equals to negative T divided by RC, where RC is called the time constant of the circuit. And then plotted a graph of ln delta V divided by delta V0 versus time, and get the value of RC to be 6 seconds, which is consistent with the direct calculation using 30 times 0.2, that is 6 seconds. The first what if question, instead of being negligible, the real emitter has resistance, although still small. This means there will be a potential spread over the emitter and the actual current will differ because now the total resistance of the whole circuit differs. For the second what if question, with no other resistor, the capacitor will get fully charged the second it connected to the battery. However, this is an ideal model and can happen in real life, as the wires and batteries definitely carry inherent resistance rather than having no effect on the circuit.